This is Voyager Notes, a transmission from 25 billion kilometers, still transmitting.
KIC 8462852 dimmed by 22% in a single transit event recorded in 2011, and that number has no clean explanation. The star sits roughly 1,470 light-years from Earth in the constellation Cygnus. Boyajian et al. Published the full anomaly in 2015, drawing on 4 years of Kepler photometry and the attention of Planet Hunters volunteers who first flagged the light curves as strange. What the instrument measured was unambiguous. What caused it remains open. The Kepler Space Telescope was not designed to find surprises. It was designed to find periodicity, the reliable clock-like dimming pattern that signals a planet passing in front of its host star. Kepler stared at a fixed patch of sky in Cygnus and Lyra from 2009 through 2013, recording the brightness of more than 150,000 stars simultaneously, every 30 minutes. Most of those stars behaved as expected. The photometry was steady, the noise was manageable, and the transit signals that emerged were small, clean, and repeating. KIC 8462852 was none of those things. The star itself is an F-type main sequence star, slightly larger and hotter than the Sun, roughly 1.4 solar masses. It had no obvious reason to be unusual. When Planet Hunters volunteers working through the Zooniverse platform began cross-checking Kepler light curves in 2011, they flagged KIC 8462852 as a dipper, a star whose brightness dropped in ways the standard transit algorithm wasn't catching. The drops were too deep, too irregular, and too asymmetric to fit the template of a planetary transit. One of the volunteers wrote in the discussion thread, "Bizarre." That word made it into the eventual paper. The light curve that Boyajian's team analyzed contained at least 2 major dimming events, now referred to as D792 and D1519, corresponding to the day numbers in Kepler's mission clock. D792 showed a brightness drop of roughly 15%. D1519 in 2013 dropped by more than 22%. For comparison, a Jupiter-sized planet transiting a star of this type would occult roughly 1% of the stellar disk. An object blocking 22% of the light from a star 1.4 times the mass of the Sun would need to be enormous, non-spherical, or multiple. None of those options mapped cleanly onto known planetary formation scenarios. This is loop hash 1. What kind of object produces dips of this shape, this depth, and this irregularity? Boyajian's team ran through the candidates in their 2015 paper, published in the monthly notices of the Royal Astronomical Society. Instrumental error was ruled out early. The signal appeared consistently across Kepler's pixels and wasn't associated with any detector artifact. Intrinsic stellar variability was considered, but F-type main sequence stars don't flicker like this. A family of comets in a disintegrating swarm became the leading explanation in that first paper, because swarms of irregular solid bodies could produce the asymmetric light curves that planet-sized disks couldn't. It wasn't a satisfying answer, it was the least unsatisfying one available at the time. The comet swarm hypothesis required a large number of bodies transiting simultaneously in a very specific geometry. The team calculated that the swarm would need to have been recently perturbed, perhaps by a passing star, to arrive in a configuration that would produce these dips. That was possible. It was also convenient in a way that made some researchers cautious. A hypothesis that requires a rare event to explain a rare observation can be self-sealing. It's hard to falsify. Then came the secular dimming. While the Kepler dipping events were being debated, a separate team began analyzing archival photographic plates from the Harvard College Observatory, covering the period from 1890 to 1989. Schaefer published a finding in 2016 noting that KIC 8 462852 had faded by approximately 0.16 magnitudes over that century, a secular decline that no comet swarm could plausibly produce. A swarm dims a star temporarily and locally. A century of fading implies something else, something either intrinsic to the star or involving a long-lived distributed structure around it. The comet swarm lost ground. The field split. Not everyone accepted Schaefer's result. A counter-analysis of the same Harvard plates suggested the long-term dimming might be an artifact of the photographic process itself, variations in plate sensitivity over time, rather than genuine stellar fading. The disagreement was not resolved. It remained a live dispute through 2017 and into 2018. What the ground had shifted to was this. The Kepler dips were real, the secular dimming was contested, and the physical explanation was still unanchored. This is where the LC, Celeste, Skara Brae, and Anchor events entered the record. These are names given to a series of smaller dipping events observed by ground-based telescopes in 2017, when the star was monitored in a coordinated campaign following predictions that it should dim again. The campaign, organized through the Las Cumbres Observatory Network, was specifically designed to catch a dip in multiple wavelengths simultaneously, because wavelength dependence is a diagnostic tool. Dust scatters blue light more than red. A perfectly opaque solid object dims all wavelengths equally. If the dips were wavelength dependent, the occulting material was dust. If they were achromatic, it was something dense and opaque. The 2017 dips were chromatic. Blue light dipped more than red. That pointed toward dust. Fine-grained, irregular, non-spherical dust, consistent with a disintegrating body or a family of them shedding material as they orbit. This was partial progress. It narrowed the class of occulting objects. It didn't identify what was producing the dust, how much total mass was involved, or why the dipping pattern was so irregular across a decade of observations. Loop hash 2. If the cause is dust, what is the source body and where is the system's known debris? The infrared record is one of the more constraining pieces. A large warm dust disk around a star would glow in the infrared. Observations with the Spitzer Space Telescope found no significant infrared excess around KIC 8462852. The star is not obviously surrounded by a dense debris disk, the way young stellar systems are. This creates a tension. Dust can explain the chromatic dipping. The absence of infrared excess constrains how much dust there can be in a steady-state disk. The dust is either transient, produced episodically by disintegrating bodies passing close to the star, or distributed in a geometry that minimizes its infrared signature. Neither is ruled out. Here is the number that resets the scale of what's being discussed. The occulting material in the D1519 event, if it were a single solid object at the estimated orbital distance, would have a cross-sectional area of roughly 13 times the surface area of the Earth. That's the size required to block 22% of the stellar disk. No known planet formation process builds an object of that shape at that scale around a mature F-type star. The number is not speculative. It follows from the geometry. It's what makes this star unusual enough to have generated more than 1,000 published papers since 2015. The secular dimming came back into view in 2018 when Montet and Simon re-examined the full Kepler dataset, including its pre-survey calibration frames, and confirmed that KIC 8462852 had faded by approximately 3% over the 4-year Kepler mission, with 2 sharper drops of roughly 2% embedded within that longer trend. This was not the century-scale fading Schaefer had proposed, but it was real, instrument-independent fading on a time scale of years. Something was changing around or within this star across the span of a single space mission. Loop hash 3, the fading over years and the irregular dipping over days, are they the same phenomenon viewed at different timescales or 2 separate processes? The intrinsic stellar hypothesis has never gone away entirely. Some models propose that material being accreted by the star or material flowing off it could produce both the dimming and the dips. Others propose a ringed or tilted disk seen nearly edge on. The problem with intrinsic explanations is that they struggle with the chromatic dipping data from 2017. The problem with extrinsic explanations, dust and debris, is that they struggle with the apparent absence of a large infrared bright reservoir. There's a third category that received attention it probably didn't deserve in the popular press: megastructures. The term was introduced as a thought experiment in the original Boyajian paper, listed alongside the other candidates as something to consider and rule out. It was not the team's favoured hypothesis. It was the one that travelled furthest from the paper. The signal to noise on that discussion was poor. What it did do was bring significant telescope time to a star that might otherwise have waited years for a follow-up campaign. The star has been monitored continuously by amateur and professional astronomers since 2015. The American Association of Variable Star Observers maintains an ongoing photometric record. The dipping continues. No 2 dips are alike in depth or duration. The aperiodicity is one of the defining features of the observation. Most natural processes produce periodicity at some level. Orbital mechanics produces periods. Stellar pulsation produces periods. The lack of any clean recurrence interval in the KIC 8462852 light curve is itself diagnostic, pointing toward a chaotic or collisional source rather than a single coherent orbiting object. The current state of the field places the most weight on the exocomet or disintegrating body class of explanations, extended to encompass a population of irregularly shaped, dust-shedding objects in a range of orbital configurations. This is consistent with the chromatic dipping, with the absence of a large infrared disk, and with the aperiodicity. It doesn't fully account for the multi-year secular fading. That piece is still being worked out. KIC 8462852 is being observed right now by ground-based telescopes across multiple continents, by amateur observers with calibrated photometric equipment, and by the ongoing archive of space-based data. The TESS mission, which began science operations in 2018, has monitored the star across multiple sectors. TESS has confirmed continued irregular variability. It hasn't resolved the mechanism. The star keeps dimming in ways that don't assemble into a clean picture. What the field has now is a constraint set, not a solution. The occulting material is dusty and irregular. It's not a single solid object. It's not a stable disk. It's probably not intrinsic to the star. The secular fading on the multi-year timescale may be related to the dipping events, or it may be a separate process entirely. The Harvard century-scale fading remains contested. The infrared non-detection is real and constraining. These data points form a boundary around the answer without identifying it. Boyajian's team has continued monitoring the star under the Where is the Flux campaign, which has gathered contributions from more than 1,700 donors and hundreds of observing nights. The name is a compressed version of the question the field is still asking. Where is the flux that should be there, and what is intercepting it? Roughly 1,470 light-years of distance sits between the instrument and the source. The light that Kepler recorded in 2011 left KIC 8462852 around the year 541 CE. Whatever process was underway at that moment, whatever structure was transiting that stellar disk, was already in motion 5 centuries before anyone on Earth was in a position to notice it. The dimming continues. The dips remain aperiodic. The secular trend is still measured in fractions of a percent per year. And the question that the 22% event opened in 2011 is still structurally open. If the occulting bodies are dust shedding and disintegrating, what is the parent body? How much mass remains in the system, and how long before the source exhausts itself and the dipping stops? Or is the dipping episodic, fed by collisional events in a belt we can't directly image, recurring on time scales longer than a human career in astronomy? We're watching something disintegrate or accrete or occult at 1,470 light-years in a system that has been in this state for at least as long as Kepler was watching. The record goes back a century in photographic plates and forward into every clear night the monitoring campaigns can secure. What it hasn't returned yet is the object at the center of it. The transit shapes are in the data. The source is not. The signal from KIC 8462852 is still irregular, still being logged, still unresolved. Which measurement in this record stays with you?
This was Voyager Notes. The signal is still coming back.